In the world of embedded systems, where resources are often limited, efficient programming is paramount. Structures and pointers in C offer a powerful synergy for managing memory and optimizing performance. These concepts are not mere programming constructs. They are the bedrock upon which robust and efficient embedded applications are built. Structures, in essence, provide a way to organize related data elements of different types under a single meaningful name. This ability to group variables logically enhances code readability and maintainability. Instead of dealing with individual variables scattered throughout the code, structures allow developers to treat related data as a single unit. Pointers, on the other hand, provide a direct line of access to memory locations. This direct access is crucial in embedded systems, where interacting with hardware often requires manipulating specific memory addresses. By using pointers, developers can efficiently read from and write to memory-mapped peripherals, access data structures directly, and optimize memory usage. Together, structures and pointers form a potent combination. They allow for the creation of complex data structures, facilitating modularity and code reuse in embedded applications. Understanding these concepts is fundamental to writing efficient, reliable, and maintainable embedded C code. Pointers in C are a fundamental concept that often proves challenging for beginners, yet they are essential for effective embedded programming. Understanding pointers is crucial because they allow you to directly manipulate memory, which is a powerful tool in the hands of a skilled programmer. In essence, a pointer is a variable that holds the memory address of another variable. This means that instead of holding a data value directly, a pointer holds the location where the actual data resides in memory. This indirect way of accessing data can be incredibly efficient, especially when dealing with large data structures or when performing operations that require frequent access to memory. The syntax for declaring a pointer involves using an asterisk before the variable name. For instance, int asterisk ptr declares a pointer named ptr that can store the address of an integer variable. The type of the pointer, in this case int, indicates the type of data the pointer is intended to point to. This type association ensures that when dereferenced, the pointer accesses the correct amount of memory corresponding to the data type it points to. This is crucial because different data types occupy different amounts of memory. For example, an integer might occupy 4 bytes, while a character might occupy just 1 byte. The pointer type ensures that the correct amount of memory is accessed. Initializing a pointer involves assigning it the address of an existing variable. This is typically done using the ampersand operator, which gives the memory address of a variable. For example, if you have an integer variable int x equals sign 10, you can initialize a pointer to this variable by writing int asterisk ptr equals sign and x. Once a pointer is initialized, it can be dereferenced using the asterisk operator to access the value stored at the memory location it points to. Dereferencing a pointer means accessing the data stored at the memory address the pointer holds. The true power of pointers shines when dealing with data structures like arrays, and more importantly, structures. They provide a way to access and manipulate data in memory directly, which is crucial for interacting with hardware in embedded systems and for creating efficient data structures like linked lists. Pointers are also essential for dynamic memory allocation, which allows programs to request memory from the operating system at runtime. This is particularly useful for creating flexible data structures that can grow or shrink as needed. In summary, pointers are a powerful feature of the C programming language that provide a bridge to memory. They enable efficient memory management, direct data manipulation, and are indispensable in embedded systems programming. Mastering pointers can significantly enhance your programming skills and open up new possibilities for creating efficient and effective software solutions. So take the time to understand and practice using pointers. They are the bridge to memory that can unlock the full potential of your programming capabilities. In many programming scenarios, dealing with individual variables can become cumbersome and difficult to manage, especially when dealing with related data. Imagine a situation where you need to handle multiple attributes of an entity, such as a sensor. Managing each attribute as a separate variable can quickly become a nightmare, leading to cluttered and hard-to-read code. Structures in C provide an elegant solution by allowing programmers to group variables of different data types under a single meaningful name. This not only simplifies the code, but also enhances its readability and maintainability. By using structures, you can encapsulate related data into a single unit, making it easier to manage and manipulate. This capability is essential for organizing complex data in a structured manner, making the code more readable, maintainable, and efficient. When data is logically grouped, it becomes easier to understand the relationships between different pieces of information, which is crucial for debugging and future development. Defining a structure involves using the struct keyword, followed by the structure name and a code block enclosed in curly braces. This syntax clearly delineates the structure's scope and its members, providing a clear and concise way to define complex data types. Within this block, we declare the members of the structure, which can be of different data types. For example, you might have an integer for storing numerical data, a float for decimal values, and a character array for strings. This flexibility allows you to create structures that closely mirror real-world entities. Struct sensor data. This code defines a structure named sensor data with three members: temperature of type int, humidity of type float, and unit of type char. Each member is defined within the structure, making it clear what data the structure is intended to hold. Each member represents a different attribute of the sensor data, grouped logically within the sensor data structure. This logical grouping is not just for convenience, it also helps in maintaining the integrity of the data by keeping related information together. This grouping makes the code more organized and easier to understand, especially when dealing with multiple instances of sensor readings in an application. For instance, if you have an array of sensor data structures, each element in the array will represent a complete set of sensor readings, making it straightforward to iterate through and process the data. Once a structure is defined, we can create variables of that structure type. These variables act as containers for the data defined by the structure, allowing you to create multiple instances of the structured data type. Each structure variable will contain its own set of member variables, as defined by the structure definition. This means that each instance of the structure can hold unique data, making it easy to manage multiple sets of related information. These members can be of any data type, making structures a versatile tool for representing real-world data in a structured format within C programs. Whether you're dealing with sensor data, employee records, or any other complex data, structures provide a robust way to organize and manage your information efficiently. Once a structure variable is declared and initialized, accessing its individual members is straightforward. This is one of the key advantages of using structures in C programming. We use the dot operator to access a member of a structure. The dot operator is a simple yet powerful tool that allows us to directly interact with the data stored within the structure. The dot operator is placed between the structure variable name and the member name. This syntax is both intuitive and easy to remember, making it a favorite among C programmers. This direct access to structure members simplifies data manipulation and enhances code readability, which is crucial for maintaining clean and efficient code. As each member can be referenced by its meaningful name within the structure, this not only makes the code more readable, but also more maintainable in the long run. Struct sensor data sensor1, sensor1.temperature =25, sensor1.humidity =55.5, sensor1.unit =C. This example clearly demonstrates how we can assign values to each member of the structure using the dot operator. In this example, we first declare a structure variable named sensor1 of the type sensor data. This declaration sets up a new instance of the structure ready to hold our data. Then we access each member of the sensor1 structure using the dot operator and assign appropriate values. This step is crucial as it populates the structure with actual data. This direct assignment using the dot operator emphasizes the ease of data manipulation within structures. It shows how straightforward it is to work with structured data in C. To further illustrate, consider retrieving the temperature value from the sensor1 structure. We would use sensor1.temperature comma, which directly accesses the temperature member of the structure, which would give us the value 25. This retrieval process is just as simple as the assignment process, showcasing the efficiency of using structures. This simple syntax highlights the clarity and conciseness that structures bring to C code, making it easier to understand and work with, especially when handling complex data sets or representing real-world entities with multiple attributes. Structures allow us to model these entities in a way that is both logical and efficient. Structures, therefore, are not just about grouping data, they are about accessing and manipulating that data in a structured and intuitive way. This approach ensures that our code remains organized and easy to follow. This structured approach is crucial for writing maintainable and understandable code, which is essential for any long-term project, particularly in embedded systems where code clarity is paramount for long-term project success. In such environments, the ability to quickly understand and modify code can make a significant difference in project outcomes.